Hello everyone, welcome to the tutorial number 13 of IIT-JAM in chemistry, and this is lecture number 9 of the physical chemistry chapter Atomic and Molecular Structure. Today's subtopic are radial and angular wave functions for hydrogen atom, radial probability distribution, shapes of s, p, d and f orbitals. Let's start with the hydrogen atom problem, or the hydrogen-like atom, with the Schrödinger wave equation, which is time independent, and according to the Cartesian coordinate in the 3 dimension, the equation is Laplacian psi 8 pi square m by h square total energy minus potential energy psi equals to 0. And as a consequence from the previous lecture, this is equation number 52. Now hydrogen atom has two particles. One is the proton in the nucleus and another is the electron. And the electron has charge minus E while the proton has charge plus E. So these two particles have some attraction force, and according to the Coulomb's law of attraction, this force is actually K Q1 Q2 by R square, and K is actually 1 by 4 pi epsilon 0, while epsilon 0 is the permittivity of vacuum, and Q1 is minus E, that is the charge of the electron, and Q2 is plus E, that is the charge of the proton. And here R is the distance between the nucleus and the electron, that is the radius of the orbit. So this is the Coulombic attraction force, and this Coulombic attraction force, if is multiplied with the radial distance, that is the radius, that is the distance of the electron from the nucleus, that is the proton, then it will get the dimension of energy, and this is the expression of the potential energy V. So the value here, the expression of the potential energy V, is minus E square over 4 pi epsilon 0 R. So we have to incorporate this potential energy value here in this equation number 52, and thus it gets the form like this. So in place of minus V, we are putting this value, and this negative sign is cancelled by this negative sign, and this becomes positive. So it is Laplacian psi plus 8 pi square m by h square into total energy, plus in place of potential energy we can write E square by 4 pi epsilon 0 R, then outside the bracket it is psi, and then it is overall 0, and this is equation number 53. And we know the relationship between the Cartesian coordinate and the polar coordinates. If x, y and z are the 3 points, are the 3 coordinates of a point on this space, then its polar coordinate values are r, theta and phi. R is actually the distance of the point from the origin, that is the radial part, and then theta and phi. Phi is the angle of the projection line of that radial line on the xy plane with the x-axis. This is phi, and theta is the angle between the radial part and the z-axis, and the range of R is 0 to R, and the maximum value of R is maybe infinity. The range of theta is 0 to pi, okay, and the range of phi is 0 to twice pi. That means it can take a whole roundabout, and this one from here to here, okay, and the relationships can easily be obtained, and these are R equals to root over x square plus y square plus z square, cos theta equals to z by r, that is theta equals to cos inverse z by r, and putting the value of r, this is the final form, cos inverse z by, in place of r it is root over x square plus y square plus z squared, and the tan phi value is nothing but y by x, therefore phi is tan inverse y by x. On the other hand, x, y, z can also be expressed in terms of r, theta and phi, and this way x is r sin theta cos phi, y is r sin theta sin phi, and z is r cos phi. So if we transform this equation number 53, that is the Schrödinger wave equation in the Cartesian coordinate, into the polar coordinate, then it takes the form of equation number 54. So this is very much complicated, so just pause the video here, take a screenshot, and then note it down in your copy. And this equation has 3 parts. One is the r function, another is the theta function, and the third one is the phi function. So it can be written in the form like this: the solution of this equation. So the value of psi, that is the wave function, is having is a combination of three different functions. So this is the r function, this is the theta function, and this is the phi function, and this is equation number 55. And if we carry forward equation number 55 in the next sheet, we can describe these different values and their dependability. So the r function is actually the distance from the electron from the nucleus, actually the probability of finding the electron, the maximum value. This is r. So definitely this will depend upon the principal quantum number and the azimuthal quantum number. So this function depends on r, and this distance, this is the distance of the electron from the nucleus, and that depends on the principal quantum number n and azimuthal quantum number l. While what about this theta function and the phi function? Let's see. Theta function is a function of theta, and it depends on these two quantum numbers. One is azimuthal quantum number l, and another is the magnetic quantum number m. While phi only depends on magnetic quantum number m. Therefore, these two parts you see here, r is dependent on n and l. Okay, while theta is dependent on l and m, as well as phi is also dependent on m. So these two can be combined as an angular function, and this can be separately written as the radial function, and thus this equation number 55 can also be written as the wave function psi is actually the radial function and the angular function. So radial function is actually a function of r, which depends on n and l, into the angular function. This is actually the total angular function, that is actually the function of theta and phi, and it depends upon the azimuthal quantum number and the magnetic quantum number. So this is equation number 56, and this equation number 56 has the two functions, the radial function, the r function, and the angular function, the a function. So the r function is known as the radial function, that depends on n and l, that is the principal and the azimuthal quantum numbers, and the angular function, a function, is the total angular wave function, that depends on the azimuthal quantum number and the magnetic quantum number. And this equation number 56 splits the wave function into two parts, and it can be solved separately. So that's all about the equation, hydrogen-like atom, and its solution. And further we can say that the value of r square, that is, this is the probability function, this r is the radial function, and its square should be actually the probability of finding an electron. So r square is the probability of finding an electron in the small volume dv near the point at which r is measured. Now this picture, this is the radial part. So suppose we are moving from the origin, that is from this is the nucleus, then we are moving outside the nucleus through this radial line. Okay, so the probability of finding an electron may be 0 here. Now it increases, and then maximum, then decreases. So this part may be regarded as the point where the probability of finding an electron is maximum. So this way, after solving these wave functions, we can easily plot them graphically, and we can easily find out the distance of the electron in its different orbits. And dv is the small volume element, okay, and it can easily be measured from this relationship. If r is the radius of the sphere, then volume is 4 by 3 pi r cube, as well as dv is the derivative of 4 by 3 pi r cube. So the derivative of 4 by 3 pi r cube is nothing but 4 by 3 pi into r cube's derivative, that means 3 r square. So 3 cancelling each other, remaining what is left, 4 pi r square and dr, definitely. So this is 4 pi r square dr. Therefore, the probability function is nothing but 4 pi r square, then the square of the r function, which is dependent on n and l, and this is actually derived from this integral. What is the integral? This is integration 0 to r square of the r function dv, and its further expression is integration 0 to r. In place of dv, we can write this value 4 pi r square dr. So 4 pi r square dr, and this is merged with the r function, and this part, which is written in bold letter, is actually known as the radial distribution function. So what is the radial distribution function? This one, 4 pi r square, then the square of the r function. And now the graphical plot, as I have said here, graphical plot from this point to further proceeding outside this origin. This graphical plot is looking like this. The characteristics of these 6 graphs are: this is the graphical plot for 1s orbital, this is for the 2s, 2p, 3s, 3p and 3d. So for 6 orbitals, these are the graphical plots, and the probability of finding the 1s electron is this one. At this point it is highest, and this is actually the Bohr radius, which is small letter a0, and its value is 0.529 angstrom. On the other hand, the 2s orbit in the 2 dimension or orbital in the 3 dimension has maximum probability here and here also. So 2 maxima, and in between these 2 maxima here is one point where it is again 0. This point is called the nodal point, and in the 3-dimensional concept it is the nodal plane, which is spherical in nature. So here is a nodal point, and this is onion-like shape. On the other hand, the 3s, it has 2 nodal points and it has 3 layers of onion. This layer is thin, this is small thick, and this is thickest. That is, the highest probability is here, but in between there are 2 more layers also, and overall there are 3 layers. This layer has highest density of electron, and these 2 are the nodal points in the 2 dimension or nodal planes in the 3 dimension. Now if we move on to the p orbital, then we shall find that it does not have any node or nodal point, but its maximum probability has shifted to the left rather than the maximum probability of 2s. That is, according to the principal quantum number, this maximum probability point increases from 1s to 2s here, from 2s to 3s, 1s to 2s here, and from 2s to 3s here. But according to the azimuthal quantum number, in the same principal quantum number, that is 2, n equals to 2 here, n equals to 2 here, but the azimuthal quantum number here, L equals to 0 and here L equals to 1, it has shifted to the left. Similarly, for the 3D orbital has no node. On the other hand, the 3p orbital, that is the next orbital from the first p orbital, so the first p orbital is 2p and the second p orbital is 3p, it has one node here, but it has 2 layers. Okay, so 1s has 0 nodes, and the radial distance of maximum probability is 0.529 angstrom, and this is known as the Bohr radius. For 2s, it has 1 node, and 2s has greater radius than 1s. So radius of 2s is greater than 1s. Actually, there are 2 radii. This one is the first one, this one is the second one, but we have to take that one which has the maximum probability, so that is this one. Similarly, for 2p, it does not have any node, and this 2p is less than 2s, but according to the principal quantum number, it is greater than the 1s. So 2p is greater than 1s but less than 2s. On the other hand, 3s is greater than 2s, as well as it has two nodal points, and three-dimensionally it has two nodal planes. And 3p has only one node here. It has two layers, and the maximum line must be greater than 2p because the principal quantum number is different. It has higher principal quantum number. But if we consider the azimuthal quantum number, then it has shifted to the left. This one existing here, this one existing a slight left. So here we can conclude that 3p is greater than 2p, but it is less than 3s. And finally, 3d. 3d is definitely less than 3p, and it is greater than 3. Actually, this is less than 3p, and 3p is less than 3s. Look, this is 3s, then 3p has shifted to the left, and 3d has further shifted to left. So this has the lowest distance. Therefore, we can conclude that this distance, that is the radius of the 3d orbital in the 3 dimension, or the 3d orbit in the 2-dimensional concept, is less than that of the 3p orbital, which is further less than that of 3s orbital. Now, what about the features of this radial distribution function? Before that, we can show you one more thing. This is 4 pi r square into square of the r function. So we have derived this as the radial distribution function. Okay, so now its features. The probability of finding the electron at the nucleus is 0. Definitely at r it is 0. If we move on to the previous picture, at the starting point there is no electron. There is no electron, no electron, no electron, no electron, and no electron. So this is 0 at 0 radius. So when r is equal to 0, you can find no electron density. The most probable distance increases from 1s to 2s. Definitely, if the principal quantum number changes, then the higher principal quantum number should have greater radius. Similarly, 3s is greater than 2s. The most probable distance decreases with respect to the azimuthal quantum number for a same orbit, as we have found that 2p has shifted towards left when compared with 2s. So here 2p, radius of the 2p orbit, is less than that of the 2s orbit. Similarly, 3d is less than 3p, which is further less than 3s, as we have discussed this. And finally, all the s orbitals except the first one, that is 1s, all the p orbitals except the first one, that is 2p, and all the d orbitals except the first one, that is 3d, all these have, similarly 4f, they do not have any node, but all other orbitals have onion-like structures, that is, they have layers. Okay, so they consist of concentric layers of electron density. There exists a nodal point or a nodal plane in the 3-dimensional concept, where now it is between the any two concentric layers. Now, feature of the total angular function, that is the a function. The total angular function a, this is independent of r, and it only depends on theta and phi. Okay, now the square of this angular distribution function, this is the probability of finding an electron at a given direction. Okay, this is not distance, this is regarding the direction, and direction is a function of theta and phi. Okay. Finally, the angular functions are plotted as polar diagrams to get the shape of the orbitals. How are the shape of the orbitals? These are the shapes of the orbitals, and these are all obtained by calculating the probability of finding electron according to the function of theta and phi. So this way we have got the shapes of the orbitals. This way 1s and 2s both are spherical in nature, but look, this is smaller than this one. And these polar diagrams do not represent at all the total wave function psi. On the other hand, the probability of finding an electron simultaneously at a distance r and in a given direction theta and phi is psi squared, such that psi squared as a function of r, theta and phi is the square of the radial distribution function as well as the square of the total angular function. And this is equation number 57, and that's all about the problem of hydrogen atom or hydrogen-like atom. Now we have to move on to the questions. So the first question: the longest wavelength of light absorbed by a hydrogen-like atom is 2.48 nanometer. The nuclear charge of the atom is what? You have to find out the nuclear charge. And given the Rydberg constant as 1,09,700 centimeter inverse. So this came in IIT-JAM 2020. And actually, for the longest wavelength, you have to, if you move from Lyman to Balmer series, then the wavelength would be longer. That is, the energy would be lesser. If you move on to Balmer to Paschen series, then again the wavelength become longer. So this way, there is no upper limit from Lyman to Balmer, Balmer to Paschen, then Paschen to bracket, bracket to Pfund. So we have to actually take the first one, the Lyman series. And for the Lyman series, in this Rydberg equation, the expression of wave number nu bar, which is actually rz squared 1 by n1 square minus 1 by ni square or n2 square. For hydrogen, this z is 1, but for hydrogen-like atom, this z cannot be, maybe or may not be 1, and we have to find the value of this z. Okay, so in order to get the longest wavelength, as I have said, we have to choose here the Lyman series. In that case, in order to find out the longest wavelength, that is the smallest energy or the lowest energy, n1 should be 1 and n2 should be 2, and the wave number is actually the reciprocal of the wavelength, and since it is given the wavelength is 2.48 nanometer, that is 2.48 into 10 to the power minus 9 meter, therefore it is 1 over 2.48 into 10 to the power minus 9 meter inverse. And Rydberg constant in centimeter unit, this is 109700, and if you add 2 more zeros, then it will become it will have the unit in the SI convention, that is meter inverse. Okay, therefore putting these values in this equation, in place of nu we are putting this value 1 by 2.48 into 10 to the minus 9, and in place of r we are putting this value in meter inverse unit. In place of z square, we have to find out this value of z. In place of n1 we have put 1, and in place of n2 we have put 2, and by solving this we have found the value of z is 7. So therefore fill in the blank by typing 7. Next question, question number 34. For hydrogen-like atoms, the ground state energy is proportional to what? These are the 4 options, where m in place of mu, mu is the reduced mass and z is the nuclear charge. So let's find out the answer. Recalling equation number 4, what was in the equation number 4? This was equation number 4 in the previous lecture, where energy of an electron is minus mass of electron, then charge of the nucleus, charge of the electron, permittivity of vacuum squared, then principal quantum number squared, then Planck's constant squared. So this is actually, here are the variables m and z, all other terms constant. If n is also made constant, then E is actually proportional to mz square. Okay, and if this m is replaced by reduced mass, then it becomes mu z square. So E energy is proportional to mu z square. Therefore the correct option should be option number C, this one. This is the right answer. Now overlap between the atomic orbital sketched below should be what type? So this is actually p pi d pi overlapping. Here the 2 lobes of the d orbitals and 2 lobes of the p orbital, 2pz orbital actually this is. But this d orbital has these two lobes with the similar wave function, whereas its anti-wave function is this one. So if this is psi, then this is psi star. So if these are positive, these are negative. So positive will overlap with positive and negative will overlap with negative. So that means this wave function is similar to this wave function and this wave function is similar to this wave function. So this is actually overlapping between two similar wave functions, that is in total it's a positive overlapping. Therefore it's a p pi d pi type of bonding overlapping, and hence it's a positive overlapping. So this is the correct option. Option A is the correct answer. And finally, this question number 36. If the normalized ground state wave function of hydrogen atom is psi for 1s equals to 1 over root pi a0 to the power 3 by 2 exponential minus r by a0, then the average distance of the electron from the nucleus in the ground state is which one out of these four options? So let's find out the answer here. The average of r, according to the fourth postulate of quantum mechanics, it is average of r integration psi r psi d tau. Here psi is actually psi of 1s, so psi 1 is r, psi 1 is d tau, and this d tau, if converted into the polar coordinate, then it can be written as r square dr sine theta d theta d phi. Here this psi 1s and psi 1s combined to be written as psi squared 1s, the limit from 0 to infinity. Then this r is this one r. Now put the value of d tau. D tau is r squared dr, then this r squared dr. Then separate integration of this theta function and separate integration of this phi function. So integration sine theta d theta, again integration of d phi. So here sine theta d theta, integration of d phi. And as I have said that the range of theta was 0 to pi and the range of phi was 0 to 2 pi. Therefore these are also the lower limit and the upper limit of the integration signs also. Okay, and the value here of this three integrals are, from the first one is 1 over pi a0 cube, then integration 0 to infinity r, then r squared, that means r cube. Okay, and here the value of psi 1s. What is the value psi 1s? This one is the value of psi 1s. Then we have taken its squared, then this root has gone, and this a to the a0 to the power 3 by 2, this half has also gone due to squaring, so it becomes a0 cube. So this is pi a0 cube. Now integration this r with this r squared and then exponential minus r by a0. So exponential minus r by a0. If this one also taken as the square form, then the 2 comes here, so it is actually in place of r, it is minus twice r. Okay, then dr, and these two remaining the same. Then finally the result of the integration is, this is the radial part, this is the theta part, and this is the phi part, and it is overall 3 by 2 a0. So the correct answer is 3 by 2 a0. So option C is the correct answer. So that's all for today's lecture. Thank you and have a nice day.